Okay, 6.1 is called integral as net change. But that is something that we've already known, okay? Bless you. When we talked about the area, bless you, in chapter 4, we said that the integral can give us the area, and area can help us find integrals. But in general, the integral from left to right gives us the net accumulation, which means signs matter. If something is above versus below, there's going to be some cancellation going on. So these are going to be applications of things that we're accumulating at different rates, like positions, velocities, raw sewage, snow, things like that. Entries on ballots for names for a baby elephant. That's another thing we're going to be accumulating in this section at variable rates. But particle motion is probably one of the most important applications. So this is essentially particle motion part 2. We've already seen particle motion when we did it from a differential standpoint, right? The derivative of position is velocity. The derivative of velocity is acceleration. Therefore, going backwards, the integral of acceleration is velocity, and the integral of velocity is going to give us some kind of position. So that's what we're going to be working towards. How can we do that? So let's look at example 1. It says a car travels at a constant velocity of 60 miles per hour in a single one-direction path along a straight road for 2 hours. It could happen. Got it? See it in mind? Constant velocity, straight road, no bends at all, one direction. And after 2 hours, how far has the car traveled? Anyone?
120 miles.
120 miles. Did you use calculus to get that answer? No. Okay? And we don't need calculus for that because the velocity, which is the rate of change, is a constant. So you could just reason it out, or you can go back to the basic rate equation that you maybe learned in 5th grade, 6th grade, 7th grade, depending on your math teacher. I call it the DIRT equation. Distance equals rate times time, and it works as long as the rate is a constant. So let's see if it works for us. Distance equals the rate was 60. Oops. You can always use stoichiometry, too, to make sure you're doing it right. 60 miles per hour times the time that elapsed was 2 hours, and that's really over 1. So hours divide out, you're left with miles. 60 times 2 is 120 miles. Excellent. Sweet. That would be boring if that's all we did today, right? So what calculus does is it gives us the powerful way to do these calculations when the rate is not constant, okay? Let's go ahead and graph. We're kind of overanalyzing what we just did now. If we were to graph the velocity in miles per hour against time in hours, what would the graph of 60 look like? A constant line. What would it look like? What kind of straight line? Horizontal. Horizontal, right? Horizontal straight line. That's what it would be. Yeah, straight horizontal line. And if we start at t equals 0 and we go to t equals 1, 2 hours, right there, what we just did is we essentially multiplied that vertical distance, 60, times this horizontal distance of 2. 60 times 2 gives us 120. So it turns out geometrically that we ended up finding the area under the velocity curve over the time interval from 0 to 2. So we now have a geometric interpretation for distance traveled, right? For a constant velocity, that's positive 60, on the interval from 0 to 2, the distance traveled over that 2-hour interval was nothing more than the area under the curve. Now, why is that important to make that connection? Well, if we had, let's say, a variable velocity, we can't find the area of this region anymore by just going rate times time, but we do have methods now for finding areas under irregular curves. And so the calculus is going to give us that. So that's what we're going to be doing in the first part of this section right here. We're going to be finding areas under curves of velocity functions and interpreting them as distances, okay? So let's look at example 2. Suppose a car travels again along a straight road. We're still going to be limited to one-directional movement, either left and right or up and down, according to now this velocity equation from 0 to 5. So the velocity now varies as a function of t squared minus 4. V is still measured in miles per hour, and t is measured in hours. First thing we want to do is sketch its graph. So let's go ahead and do that. V of t here. You want to get in the habit of putting units and labeling things, miles per hour against time in hours. And let's see, I'll choose blue. So minus 4, it's a parabola that opens up. The y-intercept is negative 4, and it opens up like that on that side. And then, of course, there's a negative side over here that we don't really need. And we're going all the way out here from 5. So we're looking at it from 0 to 5. Now, very quickly, you could probably give me the t-intercept of this function, right? If the equation is t squared minus 4, what are the 2x-intercepts for that graph? 2 and negative 2. Yeah, you set it equal to 0. 2 is the one we want. So let's kind of make sense of what's happening here. Velocity, it goes from negative to positive. So from 0 to 2, when the velocity is negative, this car is traveling in the negative direction. Let's say it's horizontal, just for convenience sake. So the negative direction would be to the left. If it were traveling on a vertical line, sometimes it says a particle is moving on a vertical line, the negative direction would be down. And then from 2 to 5, since the velocity is positive, positions are increasing. Velocity is positive means it's moving in the positive direction, which means to the right. Or if it happened to be on a vertical line, it'd be up. Okay? So we can immediately say then that this car changes directions at what time? At 2 hours, right? At t equals 2 hours, it goes from moving to the left to moving to the right because the velocity changes signs from negative to positive at 2. Okay, that's pretty cool. What's that? Yeah, so for the first 2 hours, it's moving to the left, and in the last 3 hours, it's moving to the right. And if I drew it to scale, it looks like it travels right a little bit further than it travels to the left, okay? Because the areas of these regions, as we just learned in the first example, give us the total distances it travels in those directions, yes? Okay? So let's go ahead and compute that. Example, well, the first one says to evaluate the integral from 0 to 2. So let's go ahead and write it here. We're going to work in vertical columns. So the integral from 0 to 2 of v of t dt. To evaluate it now, I'm going to go ahead and replace v of t with the equation, which is t squared minus 4. So that's a definite integral. So if we evaluate it, 1/3 t cubed minus 4t from 0 to 2. Plugging in the top minus plugging in the bottom, we get 8/3 minus 8 minus 0 minus 0. So 8 is 24/3, so you get negative 16/3. So I'm going a little bit quick here with the computations, but we're assuming that everyone knows how to do that. Now, you always want to get in the habit of putting units on your final numeric answers for these these applications. What would be the units of that? Miles, yeah. When in doubt, just look at your integral. You're doing v of t times dt. So it's units of velocity in miles per minute or miles per hour times time in hours. You get miles. Can that represent the total distance it traveled in that 2-hour period? No, you never tell people I traveled negative 16/3 miles. That's not the distance you traveled. The sign gives us the direction it traveled. So this is why it's called net change. We just found the net change in position from 0 to 2, and it ended up being a negative number. What do we call the net change in position in general? In physics, we called it the same thing, the displacement. Yeah. Now, when we did it before, we had final position minus initial position. We're not going to be doing it with position equations now. We're going to be integrating the velocity. So that's important, okay? Because the velocity could be positive or negative, the displacement is always equal to the integral, in general, from a to b of v of t dt. That's important. So just like the integral doesn't always give us the area, the integral doesn't always give us distance traveled. But what it does give us is the displacement. When you integrate velocity, you'll always get the net change in position. So you could interpret this now. On the interval from 0 to 2 hours, the car traveled 16/3 miles to the left. Okay? Or in terms of displacement, it ended up 16/3 miles to the left of where it started. All right, let's do the next one from 2 to 5. So new column here. The integral from 2 to 5 of v of t dt. Now, you don't have to integrate the whole thing again. If you want to go straight to the third line on the left column, it's 1/3 t cubed minus 4t. Same antiderivative. But now from 2 to 5, that's going to be 125/3 minus 20, and then minus, when we plug in a 2, just like we did over here, we're going to get negative 16 thirds. So if you want to simplify that, that's going to be 125 plus 16. That's 141 thirds minus 20. So to do that, 20 is the same as 60 thirds. $81 thirds? Yeah, I like that. 81 thirds. And it's positive, right? So that would be miles. So again, that's the displacement. In general, that's the displacement. We could say over the 3-hour interval from 2 to 5 hours, the car traveled 81 thirds miles to the right, or in this case, we could say it ended up 81 third miles to the right of where it started at t equals 2. Now, because it was positive on that entire interval, we could say it's moving to the right the whole time and traveled 81 third miles to the right. No, they'll ask you to find either the displacement or the distance traveled, or they might give you the integral and ask you to explain what it means. So in this case, if they just ask you to find that integral, then you just say 81 third miles and you're done. Yeah. Is that what 81 divided by 3 is? Okay. Good call. Yeah. Does the other one simplify, 16 thirds? No, 5 1/3? No. Yeah. So it does simplify. You're right. Okay. So could that give us the total distance before we move on to the next one? Could we say the total distance traveled on the interval from 2 to 5 is also 81 thirds? We actually could in this case, right? So in this case specifically, displacement and distance traveled are the same. And the only reason they're the same in this case is because from 2 to 5, what do we know about our velocity function? It is, well, not increasing, but positive, right? If your velocity is positive and you're integrating from left to right chronologically, then your velocity and your displacement are going to always be the same, always. But that's a big if. That's not always the case, all right? So in general, it gives you displacement. No, this one I only integrated from 2 to 5. So I could say on the interval from 2 to 5, the car traveled a total distance of 27 miles. I would not say on this one it traveled a total distance of negative 16 thirds. The negative kind of messes up the interpretation. Okay? Now, if I wanted to know the displacement of the vehicle on the entire interval from 0 to 5, that would be this one here. What is the integral from 0 to 5 of v of t dt? Now, because we already have both of them calculated, you could either compute this again entirely separately, or you can use that travel agent. You can go from 0 to 2, v of t dt, and then pick up at 2 and go to 5. And I would only do this because I've already computed the other two. So that would be negative 16 thirds. And then I would add to that, I'm going to put back the 81 third version. No offense to you, Trombley. And then if I combine those, that gives me 65 thirds, which I don't think simplifies to anything. But that would be miles. Okay? So could I then say that the total distance that the car traveled from 0 to 5 is 65 thirds miles? No, that's not the total distance traveled, because some was positive and some was negative. You can only say it's the same as the distance traveled if it's entirely positive from left to right. But I could say that this is the displacement. So over the displacement, there we go. Over the 5-hour period from 0 to 5 hours, the car ended up 65 thirds miles to the right of where it started, wherever it started. We don't know, but it ended up 65 thirds miles to the right of where it started. That was its net change in position. Now, with the work that we've already done, here's another question. Can I figure out what the total distance the car traveled is? Now, total distance traveled could just be listed as distance traveled. You don't really have to have the word total in there. The distance traveled or the total distance traveled wasn't 65 thirds, but is there a way to figure it out? Yeah, take the absolute value. Now direction doesn't matter. I traveled 16 third miles to the left, but I traveled 16 third miles, and then I traveled 81 third miles to the right. So I'll just make both of them positive, and now instead of canceling, I'll add them together, and I get 97 thirds miles. So this car traveled 97 thirds miles to net 65 third miles to the right of where it started. Okay? So remember that if we want total distance now, we want nothing to cancel, which would be the same geometrically as finding the what of this region? Area. Good. Just like we did with area. If you don't want anything to cancel, you make it all positive. So total distance traveled is area. So we've already written this up here. Displacement is the integral of velocity. Velocity could be positive or negative. Do you remember how to, if you had a calculator, without a calculator, if we want the distance traveled, we have to make it positive if we know it's negative. We talked about that. But do you remember if you had a calculator, how you can make the entire graph positive before you even integrate it? Well, not necessarily that. Just without even knowing what the graph looks like, just a surefire way to make sure all the y values are positive. Absolute value. I think you mentioned that a little while ago. So this right here, if you take the absolute value of your velocity function first, then take the integral from left to right, you get the area, which is the total distance traveled. We call the absolute value of velocity, we call it speed. So if you integrate the speed function, essentially, you get the total distance traveled. And this is why it's easy to see then, the total distance traveled is only the same as the displacement when velocity is already positive. We're already traveling in the positive direction from chronological order from left to right. Okay, very important then. Let's summarize. For motion, the displacement, which is defined as the net change in position, is always just the integral of the velocity function, plain old velocity. Okay, and again, units are going to be units of velocity times time, which give you position units. If you want the distance traveled, which is the gross total distance instead of the net, you have to integrate the speed function, which with the calculator is the absolute value velocity integrated. Of course, we know how to do that by hand. Now, the other thing that comes into this section is we might want to know what its position is at a certain moment. So we've already kind of done this with things. What you have at any given moment is a function of what you started with plus your net accumulation since then. It works with position as well. If you want to know where something is at a given time, call it B, and you know where it was to start with, call it S of A, then the position at B is the initial position, S of A, plus the displacement from A to B. And again, what's important is that A is your lower bound, because that's where you're starting, and that B is your upper bound, that's where you're ending up. So displacement, when added to the initial position, gives you your current location, right? If I just told you that I'm 50 miles, if I told you I was, 50 miles north of 35 from where I started, you wouldn't know where I'm at, right? Any more than if I said, hey, I drove for a while and now I'm in Austin. You wouldn't know where I started necessarily. Or I say I started in New Braunfels and I drove for a while. But if I said, hey, I started in New Braunfels and now I'm 50 miles north on 35, you'd be like, oh, you're around Austin. Yeah, right? So they're two separate things, initial position, displacement. But when you add them together, you get your current location. All right. Now we're going to work some examples. Every other problem that follows in this section is an actual AP free response question. So not only are we going to get to practice, you're going to get to start to feel what an actual free response question looks like, okay? So you'll take the multiple choice section first, non-calculator, then calculator, and you take fewer with a calculator. You take 30 without a calculator, 15 with a calculator. Then you keep your calculator out, and you break the seal on 2 questions with the calculator. So questions 1 and 2 on the free response are with the calculator. And you'll have 30 minutes, and you can move freely between those 2 questions. So you manage your time however you want, but again, on average, it's 15 minutes a question. Then you put your calculator away, you break the seal on the last 4, and you have an hour for that. So again, that's 15 minutes on average per question, but you can move around freely within those 4, and you can even come back to your first 2, but you won't have your calculator. But you can still do integral setups, put units, all that good stuff. All right, so in 2009, this was the first one on the free response. Now, I had the privilege or disprivilege of actually grading this question at the 2009 reading, which meant for about 2.5, 3 days, 8 to 9, 10 hours a day, I graded nothing but this problem right here. So I hate this problem. I hate it, okay, for more than one reason, okay? The first reason I don't like it, I started reading it back then. I'm reading it now. Karen with a C. Ugh. I cringe. Karen with a C. She's not Karen to me. She's Karen with a C. And I don't blame her. I blame her parents. Okay? In this case, her parents are the AP free response question writers. They like to kind of get cute with things. Okay? So get over the fact that it's Karen with the C. What? Karen. Call her Karen. Right. Karen. Or Saren, whatever. It doesn't really matter. So Karen with a C rides her bicycle with a B. I'm actually okay with that one. Along a straight road from home to school. You got it? She's on a bike. She starts at home. She goes to school. It even says that, starting at home at t equals 0 minutes, and arrives at school at 12 minutes. During the time from 0 to 12 minutes, her velocity v of t, and here's the units, miles per minute. Ooh, that's different, right? Not miles per hour. Miles per minute is modeled by a piecewise linear function whose graph was shown above. I threw it out here on the right. Okay, so whenever you're given a graph, an equation, or a table of values, you want to make sense of what it is, okay? And maybe anticipate the types of questions you're going to be asked. This processing can take place pretty quickly. So we have the velocity graph. I would put the units here, miles per minute. It doesn't hurt to have them. And then time over here is in minutes. So real quickly, just tell yourself that the y values of this graph are the velocities, right? The y values are the velocities. So when we have positive y values, she's moving in the positive direction, which is to or towards school. That's the positive direction because she starts at home. So positive values means she's moving towards school. Negative values, and we do have some from 2 to 4, means she's heading back towards home. Interesting. So you kind of already see that at t equals 2, she does what? She turns around. She's going towards school and then turns around and goes back home. All right, sweet. What do the slopes of velocity give you? Acceleration. So the slopes of this graph, which we can actually compute because they're line segments, will give you the acceleration. And if you had to integrate, that's units of miles per minute times minute. That's going to give you miles. That's going to give you positions that you can use to either find total distance traveled or displacements, okay? That's all you really need to do. Now we'll go ahead and look at it. It says A, B, C, D all together, but on the actual test, it'll be more like the tests I give you. You'll have part A, and you'll have a space in which to work it, okay? We're going to do everything down below. So here we go, part A. Find the acceleration of Karen with a C's bicycle at t equals 7.5 minutes. Indicate units of measure. Okay, so remember that the free response is all about not just getting the right answer, but showing your process, communicating how you got it with the correct syntax and notation. So notation, notation, notation. Accelerations are the what's of this graph? Slopes. The only equation name they gave you is v. So to communicate what you're doing, here's the minimum that you need to show. Part A, v prime of 7.5. That is the absolute least that you would need to show notationally to get credit. And now you put equals, and you mosey over to the graph. 7.5 is right here. You need to find the slope of that line segment. Now, normally, when in doubt, you would show the difference quotient. But right here, it's just down 1 square and right 1 square. So you're allowed to count. So how far are we going down? From 0.3 to 0.2 would be down 0.1. That's down 0.1. So that would be negative 0.1. And then we're running from 7 to 8, which is right 1 unit. Okay, so over 1. You can leave it like that even, right? You don't have to simplify that. Of course, anything divided by 1 is itself, so you might irresistibly have to. But wherever you decide to stop, that's where you put units. So units of slope are units of derivative. It's going to be units of y divided by units of x. So that's miles per minute divided by minute, which would be what? Miles per minute per minute. You could do it like that. Nothing wrong with that. Miles per minute per minute. But most people say miles per minute what? Squared, yeah. And that works as well. So either one of those. If you leave off the units, you're going to lose a point, okay? Whenever they remind you, indicate units of measure, that pretty much means, hey, the units themselves are a check all by themselves. And sometimes they're tied to the correct answer, meaning if you don't have them, you don't get any credit for that part. But even if it didn't say to indicate units of measure, you want to put them because they're not going to. They don't have to remind you every time. All right, so there's the answer. That also means, by the way, that her velocities are decreasing by 0.1 miles per minute each minute. Remember that? They might ask you sometimes to interpret that. So at t equals 7.5 minutes, her velocities are decreasing by 0.1 miles per minute or each minute. They didn't ask you to do that here. All right, part B, using correct units. Man, they're big on units, aren't they? Explain the meaning of this in terms of carrying with the C's trip. Ooh. And now there's a follow-up. It's just to actually find the value. But first, explain the meaning of that. What do you notice there? It's the integral of the absolute value velocity. This is the total distance traveled. Okay, now it said it with units. So here we go. The integral from 0 to 12 of the absolute value v of t dt. Try not to use pronouns, remember. Gives the total distance traveled in what units? Well, remember we're multiplying, so it's miles per minute times minute, which is in miles. We measure distance in miles, right? Not miles per minute. In miles, and here's the real easy engineering way to get full credit, from t equals 0 minutes to t equals 12 minutes. Remember, we talked about sentences and how you can kind of get all elaborate with all these modifiers and fancy terms, but you want to avoid pronouns, and you want to answer it very succinctly, okay? That gives, and I didn't say that, I wrote it out, gives the total distance traveled in miles. I graded this a bunch of time, and many people had it perfectly right, but they left out in miles. It's very easy to leave off the units on the dependent variable and just say, this gives the total distance Karen travels from 0 to 12 minutes. That wouldn't get it, would it? It gives the total distance Karen's traveled from 0 to 12 minutes. That doesn't do it because you never said the units of distance. So make sure you give units for the dependent variable as well as the independent variable, from t equals 0 minutes to t equals 12 minutes. Okay, so that's the easy way to get full credit. And then you don't go on to part C, because sometimes the letters might have more than one part. Now it's just to actually find that value. Okay, so remember with the absolute value there, it's the same as finding the area. And we practice this like crazy. In fact, your take-home test had this. Remember the easiest way to get full credit is to compute the areas in these geometric regions and then show those numbers that are positive numbers in those regions in your calculation. So you can use triangles, rectangles, trapezoids even, and sometimes circles or semicircles. It's entirely up to you. If you don't want to use trapezoids, you don't have to. So let's walk through together. You might be doing it on your own. So I'm going to go from 0 to 2. That's a triangle. So it's half the base times the height. The base is 2, so half of that is 1, times the height, 0.2, so that's 0.2. I not only write it in the region, I'm going to circle it. You don't have to circle it, but it makes it stand out a little bit more. Now, by symmetry or calculation, this area is also 0.2. On the last take-home test, some people were already putting negative 0.2 right there. You don't want to give the signs plus or minus in the regions. You want those to be positive numbers that represent areas. And then you assign correct plus or minus signs to them in your calculation, whether you're finding displacement or distance traveled. From 4 to 5, the height is 0. She didn't accumulate anything. So I'm going to go from 5 to 6 here. So I got another little triangle. The base is 1, the height is 0.3, so half of 0.3 is 0.15. And then I'm going to go with this rectangle here. It's 1 unit wide by 0.3 tall, so that's 0.3. And now on the next interval, I'm going to go with the trapezoid. But if you don't like a trapezoid, you could say it's a little triangle on top of a rectangle. I don't care. College Board doesn't care. The more numbers you write, the more numbers you're going to have show up in your answer. So this is a trapezoid that stands vertically. One height is 0.3, the other height is 0.2, so its sum is 0.5. The width is 1, so now I take half of that. Half of 0.5 is 0.25. So remember, it's half the sum times the height, which is really the width. And then from 8 to 12, I've got another trapezoid that is laying down flat. So the first base is from 8 to 11, that's 3 units. The second base is from 8 to 12, that's 4. 3 plus 4 is 7. And then the height is 0.2. So I'll just take half of 0.2, call it 0.1, times the 0.7 is 0.7. But again, if you wanted to go rectangle from 8 to 11, and then triangle from 11 to 12, whatever. So you don't have to show the computation for those areas. If you need to off to the side, that's fine. But you have to show the areas in the regions. Now let's go ahead and write it out. I'm going to do it here, and then I'll paste it down below. So the integral from 0 to 12 of the absolute value of v of t dt is equal to. Don't combine them in your head. Write them down. So it's going to be, the first one is 0.2. Is the next one plus 0.2 or minus 0.2? Plus. Good. We're finding the area, the total distance traveled. 0.2 plus 0.15 plus 0.3 plus, you don't even need the leading zeros, plus 0.25 plus 0.7. Do we have to simplify that? No. Keep in mind it's a calculator question, right? Have we even used our calculator yet? No. So if you want, with a calculator, you could type that all in and get an answer, but you're not going to get bonus points for it. So if you don't go any further than that, make sure you put units at the end of it. That's miles. That's the total distance traveled. And again, look at your integral. Velocity times dt, that's miles per minute times minutes. That gives you miles. So let me circle that, cut it, and paste it down here in part B where it's supposed to go. All right, sweet. So remember, if it's a numeric answer, you do not have to simplify. But wherever you stop, you put units. Not a very satisfying answer, but it'll work. All right, part C. Shortly after leaving home, Karen with the C realizes that she left her calculus with the C homework at home. Silly Karen thinks homework means that's where the work stays. And then she returned to home to get it. At what time? On the actual test, it was a lowercase t. At what time does she turn around to go back home? Give a reason for your answer. And that's all we're doing here. So we've kind of already figured that out, right? She turns around at what time? 2. Now, because that's the only question that they're asking on this part, you don't have to preface your answer with Karen turns around to go back home and get her homework at t equals 2. You could just say at t equals 2, but then you better put minutes. There's only one question they're asking. You're answering it directly. So it saves a little bit of writing. But now you have to say comma, since, or because, and what would be the answer? You always want to talk about a sign change in something, whether it's a first derivative for a local max or min, a second derivative for an interval of concavity, or in this case, just a sign change in a function. So since v of t, right? Since the function v of t changes from what to what? Positive to negative, not at t equals 5, but what? At, you can either say at this time, you're referring back to it, or you could just say at t equals 2 minutes again. So that would be a very judicious use of a pronoun. The antecedent to this is clearly t equals 2 minutes. So remember, you're not saying something redundant. You're saying, here is where she turned around, because that happens to be also the exact same time where the velocity, v of t, changes in this particular manner. You can't just say since the velocity changed signs. That's really all you need. They always require that you say how the sign changed. In this case, from positive to negative. Okay. And that's all they were asking on part C. So there's no follow-up question. Part D. Here's where it got a little bit creepy for me. Back when I was grading it, back in the day. Larry with an L. Larry with an L. He also rides his bicycle with a B. Also along a straight road. Also from home to school. And also in 12 minutes. Anyone getting an idea about Larry? Creeper, right? He's creeping on Karen with a C. That's what it sounds like. That's what it sounds like. Look out, Karen. Larry's velocity is modeled by W of t. So V is already taken, so they're using double V, right? W. W of t. Now, they're not giving you his graph, they're giving you his equation, and it's sinusoidal. So his velocity is like fast and slow, then fast and slow, then fast and slow. Creepy, extra creepy. Where W of t is also in miles per minute from 0 to 12 minutes. So same units and everything. All right, here's the question. Who lives closer to school, Karen or Larry? Show the work that leads to your answer. Who lives closer? Well, what do we need to know about each of them? Not what type of bike they're riding, but what? Yeah, we need to know how far they each live from school, which is not the distance traveled, which we found in part B. It's their displacement. So what they're trying to do is they're trying to bait some people who did part B. If you were to type all this in, you would get 1.8 miles, just if you're curious. We don't use that number for Karen, because Karen could literally live right across from school, you know. like an eighth of a mile away, but she just keeps going back and forth and back and forth and back and forth because she's forgetful or whatever. And Larry can actually legitimately live a lot farther away. So we need to compare their displacements. So because we're doing two different things, we want to make sure that we label it. So Karen and Larry. That would be the least you would need to do. If you want to say Karen's displacement, Larry's displacement, that says a little bit more. But you wouldn't have to do that necessarily. So remember, how do we find displacements? It's not the integral of the absolute value of velocity, but just the integral of the velocity. So for Karen, it's the integral from 0 to 12. Her velocity is v of t, dt. For Larry, it's 0 to 12. He has a special name for his. It's w of t. So you don't even have to write the expression pi 15th sine of pi 12th t right here. You certainly can, but it's a calculator question. And so because it has a distinctive name, you can give it the distinctive name. And now all we got to do is compute these. So can we just import our answer from part B for Karen's? No, we can't, okay? So now it's a matter of showing the work, but this time sign matters. So here we go. 0.2 is the first one. Now what's this 0.2 going to be? Negative 0.2. Ah, she went 0.2 of a mile away from school, had to turn around, came 0.2 of a mile back home. That makes sense. And then from 4 to 5, her velocity is 0 because she's back inside her house looking for her calculus homework. So really her trip begins anew at t equals 5 minutes. So 0.15 plus 0.3 plus 0.25 plus 0.7. So that is the work that I did up here, but I'm going to paste it down here where it needs to go. Okay, right there. And again, if I stop there, I'm going to put miles. Now, we don't technically have to simplify that, but we need to compare two numbers, don't we? So this is where you're going to want to really type that in. And if you don't trust your mind, type it into your calculator. It ends up being 1.4. 1.4. Would you put miles on that then? I would put miles on that then. I would, yeah, absolutely. Okay, and again, you have your calculator to help you with that. Now for Larry's, we already have his setup. We're only going to use his equation once. So notice this is really the first time I'm picking up my calculator. I'm picking up my calculator for the first time. Maybe I used it to help me add up the numbers for Karen. But here we go. From the home screen, by the way, make sure your calculator is in radian mode. You should be in radian mode the full time. And it should be in function mode. If you have it in some weird mode like parametric or polar, because BC's been using them, switch back to function. All right, so from the home screen, here we go. Math 9, remember, is the integral from 0 to 12 minutes. And if you had Larry's function in y1, you could just recall it by doing alpha trace, remember? But we don't have that, so we just type it in. We're only going to use it once. So you can use your horizontal division bars if you like. That's kind of a safe way to do it. I'm not going to do that because that's an extra keystroke with my mouse. So I'll just type in the equivalent. Pi x instead of t divided by 12, and then dt, which is dx. So double check, triple check, make sure that it looks exactly as you want it to look. And I actually need one other set of parentheses here, really. So I close the angle, and then that second set closes the function. Okay, so now it looks better. To open Math 9? Is that what you mean, how to get the integral? Math 9, Math 9. Yeah. And if you have your own calculator and you're not getting the math print integral, if it says F and I and T, come see me. We have to upload the math print to your calculator. All right, so once you know it's in there correctly, hit enter. You get 1.6, and I would put miles on that as well. And now we can answer the question. But you have to hit the nail on the head. You can't just go straight to your answer. You have to show, again, what you're doing with these two numbers. Like we did with the baby bird gaining weight. Remember that? Who lives closer, by the way, just for what it's worth? Karen. How do we know that? Yeah, 1.4 is smaller. So since 1.4 is less than 1.6, you don't need miles on those because now you're comparing two numbers. But if you want to, the free response is one of those times where when in doubt, do not leave it out. When in doubt, put it there. Okay, since 1.4 is less than 1.6, comma, Karen with a C lives closer. And had she not had to turn around to go back home to get her calculus homework, silly Karen, why else do you go to school? she would have gotten there in less than 12 minutes, okay? We don't even know if Larry turned around. Larry could have turned around as well. We don't know. We never even graphed his. If you want to graph it, go from 0 to 12. I mean, this would just be like if you have time to waste, whatever. You could graph Larry's. Is that right? No, never mind. I didn't have Larry's graphed in Y2, so that wasn't his graph. You don't have to graph. Yeah, I was going to say, Larry turned around quite a bit. Larry is a weirdo. Yeah, that was an old equation from another class. All right. Yeah. Okay, let's say I had it in Y1. I would hit Math 9, 0 to 12. And the easiest way to get access to your Y's is to hit Alpha Trace. It's your F4 window. Okay, and there's all of your Y's. So then you do that, and you're good. Okay? Now, you could still do it that way. This, on a free response, you're typically going to be writing your equations in Y1 and Y2. But we only used his equation one time. It's up to you if it's worth doing it that way or not. Okay, let's take a look at the scoring guidelines, because it's important for you to know how to do the problem. But as we do these, you're going to get more and more appreciative of what the actual scoring guidelines are, where they're going to be giving out points. So, and these you have access to on your own. So every problem in this section is labeled. I think on the worksheet it is as well. So you can always Google scoring guidelines, and you can even Google scoring statistics if you want to see what the average score out of 9 is. All right, so on this one on Part A, it was worth 2 checks out of 9, 1 for the answer, 1 for the units. But if your answer was there and you didn't have V of 7.5, you didn't get credit unless you had the difference quotient. Okay, notice they showed the difference quotient. You had to have one of those two in support of your answer to get credit for the answer. And then, of course, your units themselves were a single unit or check. Now, no. If you want to call it A, what that does is now you've defined the acceleration function. So if they ask you another acceleration problem later on, you could just go straight to A of. That's not important to have that. Great question. Now, someone last period said, what if you weren't sure what the answer was, but you knew the units were miles per minute squared? Could you just put miles per minute squared and get the answer check or the unit check? And the answer is no. Okay? But if you knew the units were miles per minute squared and you didn't know what the correct answer was, make up any number in the whole wide world as long as it's a real number, like 7. Okay? And now you can get the unit check. As long as it's attached to a number, you can get the unit check. So that's good to know. Not that y'all are ever going to not know what the correct answer is, but sometimes you might have a brain fart or something, or if you go back to one of those calculator questions and you can't compute the answer, but you have the integral set up, you just didn't have time to type it in, now you can go back and put 7, whatever the units are, and get credit for the unit check, all right? Sweet. All right, let's look at the next one, Part B. You got 1 check for the meaning of the integral and 1 for the value. So here it is. This integral, don't say it, the integral is the total distance, and there it is, in miles. That's what a lot of people left off, that Karen rode during the 12 minutes from 0 to 12. That we did it a little bit differently. We'd said from t equals 0 minutes to t equals 12 minutes. I would stick with the way we did it because they kind of refined it a little bit. Now, in terms of getting the right answer and communicating how you got it, if you don't do it the way we did, where you have your areas and you use those numbers down below, you have to show what the integral equation is to get that. In other words, you're going to have to split it up on your own, yucky, gross, okay? So I know for a fact that if you do it the way we did it, you're going to get full credit. But by the same token, if you're going to be finding the total distance and you tell yourself quickly in your head, 0.2 plus 0.2 is 0.4, and you put a 0.4 right here instead of a 0.2, now all of a sudden you're not going to get credit, okay? So very, very important. You have to indicate your method. Okay, the next one. Karen turns around at t equals 2 minutes. This is the time at which her velocity changes from positive to negative. So 1 check for the answer, giving the right time, and 1 for the reason. Guess what the most often given incorrect answer was? She turns around at t equals, the most often incorrect answer would be 1. Yeah, a lot of people said 1 because that's when the graph of v of t goes from increasing to decreasing. No. What actually changes at 1? Her acceleration changes from positive to negative. Yeah. in a way that I can't even explain to you, right? It's a sharp turn, so I don't know what she's doing on her bike. But they didn't ask you that. That's like physically impossible what she did right there. But we'll just let it rest. Okay. The next one. The last one, actually. Larry's distance to school was 2 points. One for setting up his integral, which was as simple as just the integral of WP dt. One for the value of 1.6 miles. And then one for saying Karen lives closer because 1.4 is less than 1.6. Now notice, they don't give the inequality here. They just say, therefore, I guarantee in today's day and age, this is 2009, this is 9 years later, they're going to expect you to see 1.4 is less than 1.6. They up their standards a little bit every year, okay? Because otherwise it might be, we're not sure what you're actually comparing. Could it be that in your mind, every time you do the second calculation is the right answer? That's a weird thing, but you're not hitting the nail on the head. You're not saying exactly what it is you're doing with your calculation. So make sure you do give that inequality for comparison purposes, all right? So there you go. Tomorrow we're going to pick up with example 4, and we're going to try and do 2 of these per day. In 50 minutes, we got 25 minutes per question. That's 10 minutes longer than what you would be normally expected to, but we're walking through it for the first time, and I'm slowing you down. So anyway, you have enough to start your homework now if you want to. Any questions or comments before we end the session?